When dozens of engineering disciplines upload their 3D models into a shared environment, tens of thousands of individual geometries rapidly collide. Information managers are tasked with navigating this dense digital space. Without a standardized language dictating how these files interact, locating a single structural flaw requires manually sifting through thousands of overlapping, unlabeled layers. Effective CAD management treats every model as a relational database, where building a strict hierarchy of searchable metadata takes precedence over the simple act of drawing lines. To impose database governance onto this chaotic environment, the Singapore standard CP83-1 enforces a precise taxonomy for organizing computer-aided design files. This standard requires every single layer to conform to a rigid, mandatory 5-field naming convention. We can decode the exact spatial logic of this standard by reverse engineering a single case study string, A__DOOR, followed by 4 hyphens, _E4. Without a syntax this strict, a federated model combining architectural, civil, and mechanical data degrades into digital noise. The first block of this string starts with the originator field. Here, the A identifies the author of the geometry as the architect. The second block is the element field. This classifies exactly what the physical geometry represents, in this case, a set of doors. The CP83 standard also accounts for trailing optional fields at the end of the sequence to denote things like project status or user-defined variables for internal company tracking. However, declaring that an architect made a door only gives us the who and the what. If you need to run a clash detection test on a 50-story high-rise, that information is entirely insufficient for 3D coordination. The true structural engine of the CP83-1 standard is the third block, the presentation field. Knowing who authored a file and what object it contains serves no mechanical purpose unless the software also knows exactly how to project that data in 3-dimensional space. The presentation field strictly utilizes a 2-character code. The first character dictates the basic classification of the data format. This initial position separates actual physical geometry from supplementary documentation. The letter A stands for annotation, the letter M for model. D is used for dimensions, and H for hatching. By explicitly isolating these codes, CP83 allows software to instantly filter out non-physical drafting elements from complex 3D clash tests. Returning to our E4 example, the first character E dictates that this layer contains physical element graphics. Yet identifying a layer as physical geometry still leaves a computational gap. The software knows the layer contains a tangible object, but it does not know the angle from which that object should be viewed. If a 2D floor plan layout and a 3D structural model occupy the exact same digital coordinate space without a sorting mechanism, the rendering engine will attempt to display both simultaneously, creating illegible visual static. Resolving this geometric conflict is the entire purpose of the second character in the presentation field. It functions as the model's spatial traffic controller. While the first character identifies the format of the information, it exists purely to build the framework necessary to assign a spatial orientation. To solve the orientation problem, CP83-1 introduces 4 primary numeric codes into the second character slot: 1, 2, 3, and 4. Code 1 dictates a front elevation view. It restricts the data to an upright, flat projection along the z-axis. Code 2 identifies a cross-section view, indicating that the graphic represents the interior cut of a structural element. Code 3 steps out of 2-dimensional restrictions entirely, defining a fully 3-dimensional or isometric view. This image shows an isometric rendering of structural I-beams in a Code 3 orientation, demonstrating how actual 3-dimensional components are anchored into the digital space. Finally, Code 4 specifies the standard plan view, looking top-down along the z-axis to show the footprint of the geometry. Looking back at our architectural string ending in E4, we can see that the number 4 explicitly forces this specific geometry to be categorized as a top-down plan view. But this creates a new mechanical challenge. We have to account for layers that inherently lack a spatial projection, such as global text notes or general drawing borders. Because CP83 requires all mandatory fields to be filled, the standard utilizes a hyphen as a wildcard character. This fills the character requirement without assigning a false spatial orientation to flat data. We can see this in a string like C__ANOTT, trailing hyphens, _D-. Here, a civil engineer creates an annotation layer specifically for dimensions. Because the text dimension has no projection, the final character is a hyphen. By utilizing specific numeric codes and a designated wildcard, the standard strips away spatial ambiguity. Every piece of geometry must mathematically declare its physical orientation. The necessity of this precision becomes obvious in a federated environment, where the architectural layout, civil grading, and mechanical HVAC systems must coexist in the exact same digital file. If every discipline uses proprietary naming conventions or conversational layer names, isolating a specific view of the building is computationally impossible. Because of the fixed CP83 syntax, an information manager can execute a wildcard search by typing *_E1* into the filter bar. The asterisk commands the software to ignore the originator and element fields completely, focusing the query entirely on the presentation data. In a fraction of a second, the software purges all top-down plan elements coded 4, all internal sections coded 2, and all isometric components coded 3 from the active screen. The resulting output is a perfectly clean, multidisciplinary elevation view, accurately extracted from hundreds of thousands of raw data points. By imposing strict numeric coding, CP83 transforms passive, static layer names into highly active global search queries. In traditional drafting workflows, operators treat their software like a digital canvas, viewing themselves as simply drawing lines and shapes on a two-dimensional plane. Adopting the CP83 standard transforms the act of drafting into the population of a rigorous, spatially aware metadata matrix. Standardizing the Z-axis through the presentation field acts as the critical bridge connecting human-readable engineering drawings with machine-readable databases. Mastering this standard does not rely on memorizing an index of acronyms. It relies on understanding the spatial logic the software uses to interpret complex information. The CP83 taxonomy forces every drawn line to declare its specific coordinate properties, ensuring information managers maintain absolute computational control over complex construction data.